Welcome to RenEnergy.com, your renewable energy and sustainability platform. Hydrogen fuel cell vehicles, a comprehensive guide to the future of sustainable transportation. Background of hydrogen fuel. Hydrogen, the simplest and most abundant element in the universe, has long been recognized for its potential as a fuel source. Its energy content by weight is higher than any other fuel, and when consumed, its only byproduct is water. Historically, hydrogen has been used in various industrial applications, but its potential as a fuel source for transportation has garnered significant interest in recent years. The concept of using hydrogen fuel cells began in the early 19th century, with the discovery of electrolysis, but it has only become a practical consideration in the last few decades as technology has advanced. Hydrogen fuel cells operate by combining hydrogen with oxygen in an electrochemical reaction to produce electricity. This process can power a variety of applications, including vehicles, without emitting harmful greenhouse gases. Importance in sustainable transportation. The transportation sector is one of the largest contributors to global greenhouse gas emissions, and a shift towards more sustainable modes of transportation is critical in combating climate change. Hydrogen fuel cell vehicles, FCVs, offer a promising solution to this challenge. Unlike conventional fossil fuel-powered vehicles, FCVs emit only water vapor, making them an environmentally friendly alternative. Moreover, hydrogen can be produced from a variety of renewable resources, such as wind, solar, or hydroelectric power, further reducing the carbon footprint of transportation. The adoption of hydrogen fuel cell technology in transportation also aligns with global efforts to reduce dependence on oil and promote energy security. By diversifying the energy sources used in transportation, countries can become more resilient to fluctuations in oil prices and supply disruptions. Basic principles of hydrogen fuel cells. Electrochemical process. Hydrogen fuel cells operate on an electrochemical process that converts chemical energy into electrical energy. At its core, the process involves the combination of hydrogen and oxygen to produce water, releasing energy in the form of electricity. Anode reaction. At the anode, hydrogen gas, H2, is split into two hydrogen ions, protons, and two electrons. The protons move through a proton exchange membrane towards the cathode, while the electrons are directed through an external circuit, providing electrical power. Cathode reaction. At the cathode, oxygen from the air is combined with the protons and electrons to form water, H2O, the only byproduct of the reaction. Overall reaction. The overall reaction in a hydrogen fuel cell can be summarized as 2H2 plus O2 2H2O plus energy. This reaction is highly efficient and does not produce harmful emissions, making it an attractive energy conversion process for various applications. Components and structure. A hydrogen fuel cell consists of several key components, each playing a vital role in the electrochemical process. Anode. The anode is where the hydrogen gas is introduced and split into protons and electrons. It is usually made of porous materials coated with catalysts, such as platinum, to facilitate the reaction. Cathode. The cathode is where oxygen from the air reacts with the protons and electrons to form water. Like the anode, it is made of porous materials and coated with catalysts to accelerate the reaction. Proton exchange membrane, PEM. The PEM allows only protons to pass through, directing them from the anode to the cathode. It acts as a separator between the two electrodes, preventing direct electron flow and forcing electrons through the external circuit. Electrolyte. Some types of fuel cells utilize an electrolyte solution that helps in conducting ions between the anode and cathode. Bipolar plates. These plates are used to distribute gases evenly across the electrodes and act as current collectors, directing the flow of electrons through the external circuit. Cooling and humidifying systems. Proper temperature and moisture control are essential for the efficient operation of the fuel cell, and these systems ensure optimal conditions. Types of hydrogen fuel cell vehicles. Passenger cars. Hydrogen fuel cell passenger cars are designed for individual or family use. These vehicles are typically equipped with a hydrogen fuel cell system that powers an electric motor, offering a driving experience similar to that of traditional gasoline-powered cars but without harmful emissions. Major automotive manufacturers have been investing in the development of fuel cell passenger cars, and some models are already available in select markets. The key benefits of hydrogen fuel cell passenger cars include zero emissions. The only byproduct is water vapor. Long range. Compared to battery electric vehicles, they often offer a longer driving range. Fast refueling. Refueling can be done in just a few minutes, similar to gasoline refueling. Buses and commercial vehicles. Buses and commercial vehicles powered by hydrogen fuel cells offer a promising solution for public transportation and fleet operations. These vehicles are typically larger and require more energy, making hydrogen an attractive option due to its high energy density and quick refueling capabilities. Cities around the world are exploring hydrogen fuel cell buses as part of their efforts to reduce urban pollution. Advantages of fuel cell buses and commercial vehicles include reduced emissions, ideal for densely populated urban areas where air quality is a concern. Scalability, suitable for various commercial applications, including delivery trucks and heavy-duty transport. Potential cost savings, though initial costs are high, potential fuel and maintenance savings may make them economically viable in the long term. Specialty and industrial vehicles. In addition to passenger cars and buses, hydrogen fuel cells are being used in specialty and industrial vehicles, such as forklifts, mining equipment, and even trains. These applications showcase the versatility of hydrogen fuel cell technology. Benefits in this category include versatility, can be customized for various specialized tasks and heavy-duty applications. Energy efficiency, offers improved energy efficiency compared to traditional diesel-powered industrial vehicles. Sustainability, supports organizational goals for sustainability and environmental stewardship. Hydrogen production and storage. A. Production methods. Hydrogen can be produced through various methods, each with distinct advantages and challenges. Steam methane reforming, SMR, this is the most common method for producing hydrogen commercially. Natural gas is reacted with steam, resulting in hydrogen and carbon monoxide. Further reaction with water converts the carbon monoxide to carbon dioxide, leaving pure hydrogen. While efficient, this method does produce greenhouse gas emissions. Electrolysis. Electrolysis involves splitting water into hydrogen and oxygen using an electric current. When powered by renewable energy sources, this method can be a completely clean way to produce hydrogen. Biomass gasification. Biomass materials, such as agricultural residues, can be gasified to produce hydrogen. This method can be carbon neutral, depending on the feedstock used. Thermochemical water splitting. Using heat, often from solar energy, and chemical reactions, water can be split into hydrogen and oxygen. This process is still in the experimental stages but holds potential for sustainable hydrogen production. Photoelectrochemical, PEC, water splitting. This method uses solar energy to directly split water into hydrogen and oxygen. It's a promising but still developing technology. Storage and distribution. Storing and distributing hydrogen is a critical aspect of making hydrogen fuel cell technology practical and widespread. Here's how it's done. Compression. Hydrogen is often compressed to high pressures to reduce its volume for storage and transport. This requires significant energy but is a well-established method. Liquefaction. Hydrogen can be cooled to extremely low temperatures to become a liquid, further reducing its volume. This method is energy intensive but can be suitable for long-term storage. Metal hydrides and chemical hydrogen storage. These methods involve storing hydrogen in solid or liquid chemical compounds, potentially offering higher storage densities. Distribution infrastructure. The development of pipelines, refueling stations, and other infrastructure is essential for delivering hydrogen to where it's needed. Efforts are underway in various regions to build this infrastructure, but it remains a significant challenge. Safety considerations. Hydrogen is flammable, so careful handling, storage, and transportation are essential. Standards and regulations are in place to ensure safety. Fuel cell system in vehicles. Integration with electric systems. The integration of fuel cell systems with electric systems in vehicles is a complex but vital aspect of fuel cell vehicle, FCV, design. Here's how it generally works. Fuel cell stack. The fuel cell stack generates electricity through the electrochemical reaction of hydrogen and oxygen. This is the core of the fuel cell system, converting chemical energy into electrical energy. Electric motor. The electricity generated by the fuel cell stack is used to power an electric motor, which drives the wheels of the vehicle. Battery or supercapacitor. Many FCVs include a battery or supercapacitor that stores excess energy from the fuel cell or regenerative braking. This stored energy can provide additional power during peak demands, such as acceleration. Power electronics. The power electronics manage the flow of electricity between the fuel cell, battery, electric motor, and other components. They ensure that the right amount of power is delivered to each part of the system as needed. Thermal management system. Fuel cells generate heat, so a thermal management system is necessary to keep the fuel cell at the optimal temperature. Controls and software. Sophisticated controls and software manage the overall operation of the fuel cell and electric systems, optimizing efficiency, performance, and safety. Hybrid configurations. Hybrid configurations combine a fuel cell system with another power source, typically a battery or an internal combustion engine. These configurations provide additional flexibility and can enhance efficiency and performance. Fuel cell battery hybrid combines a fuel cell with a battery, allowing the vehicle to draw power from both sources. The battery can store energy from regenerative braking or provide extra power for acceleration, while the fuel cell provides consistent energy for cruising. Fuel cell plug-in hybrid. Similar to a fuel cell battery hybrid but includes the ability to charge the battery from the electrical grid, offering additional flexibility and potential efficiency gains. Fuel cell internal combustion engine hybrid. Some experimental designs combine a fuel cell with a traditional internal combustion engine. The fuel cell can provide energy for cruising, while the engine provides additional power as needed. Environmental impact and benefits of hydrogen fuel cells. Emissions. One of the most significant advantages of hydrogen fuel cells is their potential to reduce harmful emissions. Zero tailpipe emissions. When using pure hydrogen as fuel, the only byproduct of the fuel cell reaction is water vapor. This means zero tailpipe emissions of pollutants like carbon monoxide, nitrogen oxides, and particulates, which are common in internal combustion engine vehicles. Greenhouse gas emissions. The overall greenhouse gas emissions depend on how the hydrogen is produced. If generated from fossil fuels like natural gas, some CO2 emissions are involved. However, if hydrogen is produced using renewable energy sources such as wind or solar power, the entire process can be virtually carbon neutral. Potential for air quality improvement. In urban areas where air quality is a significant concern, hydrogen fuel cells can offer a substantial benefit by eliminating tailpipe pollutants. Energy efficiency. Hydrogen fuel cells also offer advantages in terms of energy efficiency. High efficiency. Fuel cells are generally more efficient at converting fuel energy into useful work compared to internal combustion engines. They can achieve efficiencies of around 40 to 60%, whereas conventional gasoline engines are typically around 20 to 30% efficient. Energy recovery. Some fuel cell vehicles use regenerative braking systems that capture energy typically lost as heat during braking and store it for later use. This further enhances the efficiency of the vehicle. Integration with renewable energy. Hydrogen can be produced using renewable energy sources, and fuel cells can, therefore, be a part of a sustainable energy ecosystem. When renewable energy is used to produce hydrogen, the overall energy chain can be highly efficient and environmentally friendly. Economic considerations of hydrogen fuel cell vehicles. Cost of ownership. Owning a hydrogen fuel cell vehicle, FCV, entails several economic factors. Purchase price. As of now, FCVs tend to be more expensive than their internal combustion engine counterparts, primarily due to the high cost of fuel cell technology and low production volumes. Fuel costs. Hydrogen fuel prices can vary significantly depending on location and production method. Generally, hydrogen fuel tends to be more expensive than gasoline per mile driven, though this may change with increased production and distribution. Maintenance costs. FCVs typically have fewer moving parts than traditional vehicles, which can translate to lower maintenance costs. However, specialized servicing might be more expensive if there's limited availability of qualified technicians. Incentives and subsidies. Many regions offer incentives for purchasing FCVs, such as tax credits or rebates, which can significantly reduce the cost of ownership. Resale value. The resale value of FCVs is still uncertain due to the relatively new technology and limited market. This factor may influence long-term cost considerations. Market trends. The market for hydrogen fuel cell vehicles is evolving, and several trends are shaping its growth. Increasing adoption. As technology advances and costs decrease, more consumers are considering FCVs as a viable option. Various automakers are investing in hydrogen technology, expanding the available choices. Infrastructure development. The growth of hydrogen refueling infrastructure is a crucial factor in the market's expansion. Efforts to increase the number of refueling stations are underway in several regions. Government policies. Many governments are promoting hydrogen technology through regulations, incentives, and public-private partnerships, aiding market growth. Corporate fleets and public transport. Several companies and cities are integrating FCVs into their fleets and public transportation systems, fostering market acceptance and technological development. Integration with renewable energy. The connection between hydrogen production and renewable energy sources is fostering synergies that can drive down costs and enhance sustainability, further propelling the market. Challenges and solutions. Infrastructure development. Challenges. Limited refueling stations. Without widespread hydrogen refueling stations, potential buyers may be deterred, limiting the usability of FCVs. High costs. Building the necessary infrastructure for hydrogen production, distribution, and refueling is capital intensive. Logistical complexities. Hydrogen requires specific handling and equipment for transporting and storing, adding to the complexity of infrastructure development. Solutions. Public-private partnerships. Collaborative efforts between governments and private companies can spur infrastructure development through shared investments and incentives. Regional planning. Targeting development in key regions can create hydrogen corridors, supporting growth in specific areas. Technology advancements. Research and innovation in storage and distribution technologies can reduce costs and facilitate infrastructure growth. Technological challenges. Challenges. Cost of fuel cells. Fuel cells materials and manufacturing processes can be expensive, especially due to the use of precious metals like platinum. Durability and reliability. Ensuring the long-term performance and durability of fuel cells remains a challenge. Efficiency of hydrogen production. The efficiency and environmental impact of hydrogen production can vary significantly depending on the method used. Solutions. Research and development. Continued investment in R&D can lead to innovations that reduce costs, enhance durability, and increase efficiency. Standardization. Implementing standards for components and systems can foster competition and drive down prices. Alternative materials. Exploring alternative catalyst materials may reduce reliance on expensive and rare elements, decreasing costs. Thank you for choosing ReneEnergy.com as your go-to source for all things renewable energy and sustainability.